Good afternoon, I am Mr. Ish. Thank you for joining me for this video. In this video, we are looking at a reverse procedure where we have to find a set of parametric equations from a given description, because that description will help you develop a rectangular equation. You'll take that rectangular equation and demonstrate from that a set of parametric equations which would satisfy it. Contrast what you're seeing today with the previous two videos on parametric equations, where utilizing a set of parametric equations, we were developing the rectangular equation. Here we're doing a reverse procedure, so you have to learn how to work backwards. We are looking everything here with regards to three questions: one circle, one ellipse, one hyperbola, and you'll see how you work backwards. When you're looking at circles and ellipses, you want to focus in on this identity: cosine squared theta or t plus sine squared theta or t is equal to 1, because you can very well develop that. Think about the circle and the ellipse equation. There's always a positive in there. So let's look at this. When you're given a description, your first goal is to demonstrate a rectangular equation. You know, for a circle, you're always looking at it in terms of this, and this right here is what will enable you to develop that rectangular equation. We have the center, the x and y component, or the h and k, and you just plug them in. You have x minus 2 whole square plus y minus 2 whole square is equal to 4 square, which is 16. Now what you want to do in these type of questions where you have to find a set of parametric equations, consider this either sine square or cosine square, but we can focus this on as a cosine. You want to make this look like a cosine squared theta, you want to make this look like a sine squared theta is equal to a 1. And that right there will guide you into what this x should be in terms of a parameter and what the y should be in terms of the parameters that will come in. Think about it. If I only want to see a cosine squared theta here and I only want to see a sine squared theta here, then these minus 2's should be cancelled out by some item which is coming in through the parametric equation. If you were to see this parametric equation would be 2 plus, and I want to somehow demonstrate a 16 come out over here in terms of coefficients, because that 16 would isolate and it would very well be identical to that. Then you're really thinking about this: 2 plus 4 cosine theta. And then here you're really looking at 2 plus 4 sine theta, and these would be your answers right over here. This would be your one parameter and this would be your other parameter, but you can test them out. When you put everything here in places of x and y, you see what happens. You have 2 plus 4 cosine theta minus 2 whole square, and then here you put the y value: 2 plus 4 sine theta minus 2 whole square is equal to 16. These 2's will cancel out. You'll end up having here 16 cosine squared theta, which is what I wanted to see, and here you'll have a 16 sine squared theta, which is what you wanted. You'll have the 16 isolate, then you'll have your identity here: cosine squared theta plus sine squared theta is equal to 16. The 16's cancel out, so you have this identity equal 1, and that right there is good. So this right here is indeed working out in our favor, so we know these parametric equations are right. But remember how everything has played out. This right here is our answer for this specific question. Now check this out. We have an ellipse over here which has vertices plus and minus 4 comma 0, focal points plus and minus 3 comma 0, and we have to develop a set of parametric equations. How can we do that? Well, if you were to graph this out, it would very much guide you into the procedure. If the vertices are right over here and you know you're looking at a horizontally directed ellipse, you know the vertex or the values are associated with the A, the focal points with the C. Here you're looking at a 4, here you're looking at a 3, everything is centered around the origin. You know you have to find the B value, and B value is coming from C square is equal to A square minus B square. You'll have 9 is equal to 16 minus B square is equal to minus 7, B square is equal to 7, and B is equal to root 7. So you've gotten your B value, but you're looking at an equation form which is x square over a square plus y square over b square is equal to 1, and you very much can develop cosine square plus sine square equals 1. You can see here a cosine square, here's my sine square, and here's my equal to 1. You have to bring it in that way. But first, develop your rectangular equation by plugging in the values. You have a x square over a square, which is 16, plus y square over b square, which is here 7, is equal to 1. I need to somehow develop this into cosine squared theta plus sine squared theta equals 1, and those would be your parametric equations coming into play. X, if I were to put a 4 over here and a cosine theta, and for y I would put a root 7 and a sine theta, it would work out. Because when I substitute these in here, look what would happen. You'd have a 4 cosine theta whole square over 16, which is your a square, plus y square, which is this root 7 sine theta whole square over the 7, which is your b square, is equal to 1. This will become a 16 and it'll cancel out. This will become a 7 and it'll cancel out. You'll be left only with the identity cosine squared theta plus sine squared theta is equal to 1, and that would be all that you would want. So these parametric equations here are good, and that right there would be your answer to this question. Let's look at how everything would work out with regards to hyperbola, and then we can be done with this video. Alright, let's check this out. We have a hyperbola over here with the center minus 3 comma 2. You have these vertices and you have the focal points. You didn't need to even be given the center. You could have easily determined it here from the midpoint. The midpoint of this right over here would be 0 plus minus 6 divided by 2, which is a minus 3. And then 2 plus 2 divided by 2 is a 2. 2 plus 2 divided by 2 is a 2. That would be your center. Your center is right here, minus 3 comma 2. And your vertices are 0 comma 2 and minus 6 comma 2. You have a focal point. Remember, for a hyperbola, the focal points are located further away from the center than are the vertices. You have one here, minus 7 comma 2 and 1 comma 2. You have a hyperbola which would look something like this, a horizontally directed hyperbola. Your equation over here is of this form: x minus h whole square over a square minus y minus k whole square over b square is equal to 1. You just have to first develop your rectangular equation. This x minus h over here, would that become x plus 3 whole square over a square? We'll figure that out. And y minus k here would be y minus 2 whole square over your b square is equal to 1. When I'm looking at this, the distance from the center to each of these vertices is your a value. You're looking here from the center, minus 3 to 0 or minus 3 to minus 6. It's a distance of a 3. And your c value is, of course, the distance from the center to the focal point. When you're looking here from minus 3 to minus 7 or minus 3 to 1, you're looking here at a distance of a 4. You know, for hyperbola, c square is equal to a square plus b square. You have a 16 is equal to a square, which here is a 9, plus b square, and then b here is incidentally coming out to be root 7. So it's working out to be same numbers. Anyhow, let's plug in the values: x plus 3 whole square over a square, which is a 9. Y minus 2 whole square over b square, which is a 7. And now you have to basically develop a set of parametric equations. But now what is your guide? It's no longer sine squared theta plus cosine squared theta equals 1. Look at this. You need to be thinking about something. If you were to take this on the other side, look what would happen. You'll have x plus 3 whole square over 9 is equal to 1 plus y minus 2 whole square over 7. This looks very much like a secant squared theta is equal to 1 plus tan squared theta type of identity. Secant squared theta is equal to 1 plus tan squared theta. That's what I want to be thinking about. My parameter should follow that route. X here should be equal to, I need to cancel out that 3. How about I do minus 3 and I need to bring a 9 into my numerator. It will be 3 secant theta. When I'm looking here at my y, I need to cancel out that minus 2 with a plus 2. And then I need to bring in a 7 here in the numerator, which would cancel out with the denominator. I'm looking here at 2 plus root 7 tan theta, and that right there would be my two parametric equations. But I want to test them out, and I'm going to test them out for you right over here. When I test them out, I have this coming in the numerator and this here in the other numerator in places of x. Here I'm getting a minus 3 plus 3 secant theta plus 3 whole square over 9 is equal to 1 plus, I'm going to put this right here in place of that y over here. I'll have a 2 plus root 7 tan theta minus 2 whole square over 7. This minus 3 and this 3 will cancel out. This 2 and this minus 2 will cancel out. You'll have a 9 secant square theta over 9 is equal to 1 plus root 7 tan theta whole square will be 7 tan square theta over 7. The 9s will cancel out, the 7s will cancel out. You'll have a secant square theta is equal to 1 plus tan square theta, which is what we wanted. So it confirms the fact that these parametric equations are good. X is equal to minus 3 plus 3 secant theta and y is equal to 2 plus root 7 tan theta. Remember, again, for a circle and an ellipse, you want to use a sine square theta plus cosine square theta equals 1 identity. But for a hyperbola, because we have a minus involved, you want to be thinking about this identity. And in this video, I wanted to show you these three questions, and we've shown you these three questions, the procedures involved in working in a backwards direction from a rectangular equation to your parametric equation. So you should know how to do that. Thank you for watching. Have a nice day.